Next speaker is John Kim from UCLA, also my former colleague at NASA Ames, and on physics and control of all turbulence. John, thanks.
Two comments before I start. One, if anybody read my abstract, which Joe Kloecki complained it took 20 minutes to read, I am not actually going to talk about that. I'm going to have a condensed version of it, and then we'll talk about something else, because Ivan Maruzi asked me to review a paper for JFM, and I took it with me, and then I read on the airplane, and I found out this is a follow-up work we did a couple of years ago. There's some interesting and misunderstanding of our results. I want to actually talk about that after going quickly over the stuff on the abstract. And also, the yesterday and today's discussion we have had reminds me of my first turbulence class at Brown University, which is about 35 years ago. Joe Brown started this turbulence class saying that I'm going to teach you about turbulence, what I know. I think it is true, but it may be all wrong. And at the time, I was a student, I thought it was a very odd comment, but then, well, today or yesterday, we talk about everything I know about turbulence. We still open question, log, common constant, and all that. So even probably the content of the presentation I'm going to present also probably is a still open question. This is based on my limited observation and limited or biased opinion. So with that caveat, I'll start. And just, this is another number that you can use. We all know how important that drag reduction business. This is a slide I actually made a couple of years ago that for example, ocean shipping consumes about 2.1 billion barrels of oil. And at the time, it was $60. And a couple of weeks ago, I was preparing this, and it was like $140. Well, now it came down about $100. But whatever number you want to put in here, the saving is quite drastic. So that's why it's an important, serious business. And then there are several advancement understanding of turbulence itself, and also numerical simulations, and then now the sensor and actuator technology make it all this thing actually coming close to the realization of doing. But one point I want to make is I think the contribution of numerical simulation, which is still very limited to the very low Reynolds number, I don't think it will be coming from pushing up the high Reynolds number simulation, because we're still very limited and low end. Well, I think the real contribution will be coming from, if you can design, I'm going to show a couple of examples, some very clever numerical experiment, which may or may not be possible in physical laboratory, and also maybe some dealing with the flow that may not exist, but it's designed such a way that you can actually learn some of the flow physics from it. I think that's where actually the large contribution from numerical simulation will be coming, and I'll be showing a couple of examples of that in this talk. So this is, we all know, and you can ask several questions. We have already addressed some of these issues, that why turbulent boundary layer has such a high skin friction and low, the laminar flow at the low. And I don't think we really understood this, even though we knew this curve for 100 years, almost 100 years, but I don't think we really understood the mechanism between these two flows, and I don't think still we completely understand. There's still some open question. And the other question that I'm going to address, that is why I changed the talk, is, from a control point of view, it's nice to know what is actually lower bound. What should be our target? Is this laminar flow is the one actually the lowest possible flow, that should be our optimum target? And so that's something that I'm going to address after going quickly over the stuff that. So, this is again probably for this audience we don't need it, but the point I want to make is, if you look at the turbulent boundary layer, skin friction is not high everywhere. Okay, it's just the regions of the small regions of very high skin friction, and when you add it up, and that's the turbulent, the skin friction average is high. Now, if you cut across this now, every region that has a high skin friction is related to or highly correlated with the streamlined vortices. And this is looking at into the board and the lower wall and upper wall, you can see the concentration of the streamline vortices, and they're the one that causing these patches of the skin friction. So the control strategy has been targeting this particular structure. And if you look at some of the drag reducing the flow field, including those that Ron just mentioned, compared to the regular channel, which is this lower Reynolds number channel looking into the cross section, you see that the streamline vortices near the wall. But if you apply some sort of control, this is the LQR technique that I'm going to just briefly mention that, and the polymer reduce the flow, and the hydrophobic surface, we did some simulation on that. It's all the bottom line, when they reduce the drag, and this is either the streamline vortices disappeared or the strength has been greatly reduced. It's very much related to the existence of the streak, and so this is exactly the same thing here. And here's some examples of the various people trying to explain why they get drag reduction through the influence on the streamline vortices. This is Duvieff et al. In Stanford group. And even the microbubble, there's still the open question whether or not microbubble indeed to reduce the drag or not, but those who observed it numerically and experimentally still explaining in terms of the effect on the streamline vortices. And so our explanation also why the hydrophobic surface reduced the skin friction drag was also related to the streamline vortices. And here's the one evidence that we've done some years ago, the simple idea of this, if the streamline vortice is causing a large skin frictions, they can do the controls, what is known now is opposition control, then you reduce the strength of the streamline vortices, then that indeed reduce about 30% of skin friction reduction. So just to summarize this, I guess actually I can skip that part, but the one part that maybe now the RBM may not agree based on their recent simulation or not, but the characteristic of the streamline vortices are actually quite independent from what's going on outside the outer layer part. So what they did is some clever experiment. This is an example of what I mean by clever experiment, which you cannot do it physically, but they modified the Navier-Stokes equation in such a way they remove by filtering out some large-scale structures outer part, and then see what happened to near the wall, and they see almost kind of no difference between the two, so they sort of conclude the influence, whatever the outer part, whatever it is, it's a secondary fact. I think that's a nice example of what the numerical experiment can shed the light. So that also is a kind of, we've done something similar work. This is something that we have proposed, and I think you have some variation of this you have seen yesterday and today. So what we call at the time the self-sustaining mechanism of neural turbulence. You can start anywhere you want, but you can start from a streamline vortices, and then that creates the streaks, and streaks are being unstable, and they created the streamlines varying the disturbances, which is essential to maintain this streamline role, which is independent of streamline direction, which in itself cannot be sustained. So this is a sort of generally now the accepted the mechanism. There's some variation, for example, Fadil Hussein and his student, in addition to the breakdown due to the normal mode instability, they also emphasize that maybe the transient growth of this is also important, and also the nonlinear interaction due to this convection type, roll type of motion that emphasize the streamline vortex stretching is more important. But overall pictures, I think, is kind of still the same. So what to recognize is the following. Out of these three critical the process, these two are actually linear process, and these are the nonlinear. Okay? So once you have to identify the linear mechanism, then that actually gives us some better way to handle how to go in there and to break this the cycle. So one experiment we did is again numerical experiment. So this is not a real flow that we call the virtual flow. What if I go there, okay, I break this cycle over here? This you can think about it as a kind of an artificial flow, or you can think about what later on we talk about that. Somehow you have a control mechanism that actually prevent this creation of the streak from a streamlined roll. So what that happens. So this is what we call the virtual flow, and I just how you do that. And this is a full Navier-Stokes equation. We still keep the nonlinear term. This is nonlinear simulation, but we're going to just get rid of that coupling term between the wall normal component and the streamlined Bertizzi component. That's the one that the streamlined roll created a streak, and see what happened that. So that is what we did, and then I'm just going to show the short. Oops. The cross section, you're looking at the cross section and upper wall, lower wall. It is a regular channel without that linear coupling term. That first the structure disappeared and then will become a completely laminar flow. This particular case, a low Reynolds number now, so in high Reynolds number, you may or may not completely relaminize. But the key point is, even you do the full nonlinear simulation without that linear leg part, that the flow cannot be sustained. So this is a key part of that self-sustaining mechanism. So once you recognize, okay, this is a linear system, at least the part that I'm interested in is a linear system, then I can actually do, using a linear system theory, to design a controller, and then formally design the controller based on the linear system theory. I was going to talk a little bit more about this, but since I'm going to talk about the other part, I'm going to go very quickly, and then I think Dan's also probably talk a little bit about this, so probably that should be okay. So you can formally recast the Navier-Stokes system into the so-called state space representation. Then you can define the object function or cost function. Then you can, what do I do to minimize this cost function? And there is a standard procedure of how to create the control input. That is, U is a control input to that system. And then you can, in real system, that you cannot assume that you know everything about the flow state, so you have to base on some limited measurement. So if you use a limited measurement of y, then how do you construct the estimation of actually what's going on? And that I just want to skip that part, and then part two. And you apply, this is a channel flow, what the controller will give you, what the control input, the U should be, and then is that me? And you can construct the various controller to minimize. I mean, the obvious one, you try to minimize the energy, or something that I did artificially. This is a linear coupling term. I saw that if you were a perfect controller, then this will make it a fully turbulent flow into laminar stage. But obviously, that controller will not be that successful. So, but you can have a various controller. Then just one example here that we just to show that in spite of the system itself is a linear, I mean the nonlinear, that the linear controller computer froze. But take my word, and if you drag of the regular uncontrolled flow, they'll oscillate that, and the reduced flow will oscillate on that. So this to show that we designed it based on the linear system, but that the controller works reasonably well. You missed that the animation, but this is a result of in terms of drag curve. Here comes now a change of my talk, and I wasn't going to talk about too much about this, and this is something that I changed on the plane from LAX to London to change my talk. This is could be advantage or disadvantage having the laptop with you and then change this slide on the spot. So from a controller point of view, it would be nice if I know what is my limit, so that I should have some sort of a target that the ideal set. What is the minimum drag in a wall-bound turbulent flow? Is it laminar flow? Is it would normally expect? Now this work actually, we did find this serendipitously, because we're looking for some what the control people call the periodic control. We want to, instead of based on some steady state, we want to drive our system in a periodic state and then apply the control based on that. So And during that process, we applied the blowing and suction at the wall, the various different wavelengths and various different wave speed. And this particular case, when you have a traveling wave upstream, this is a two-dimensional simulation. I'm going to show that the turbulence simulation later on. We do get this drag, what we call drag, below that of laminar value. In this normalization, laminar value is 2, and this is certainly below 2. And not only that, it's not just a transient, it's sustained. This was a quite surprising result. And on top of that, we ran into this Bewley's conjecture a few years ago. He was questioning the same question, whether or not you can have a sustained drag that below that of a laminar. And then he concluded that, say, suppose you do some blowing and suction just the way we do it with a net zero mass flux. What is the minimum drag you can have? And he conjectured that the lowest sustainable drag is that of laminar flow. So it's totally contradictory with the Bewley's conjecture. Now, if you look at the skin friction in the fully developed channel flow, you can actually derive this formula, which is, I think, done first Nogagata and Bewley also. Whatever the drag of the actual flow is the base flow of the laminar plus this quantity. This is a y-weighted average of Reynolds shear stress. So the question of whether or not you can get the laminar drag below that of laminar value is whether I can have this Reynolds stress structure such that this y-weighted average is a negative. So this is all boiled down to whether or not this quantity I can drive to the negative. Normally, in a turbulent flow, for example, u prime, b prime is negative, y is negative in this coordinate system. This is a positive. That's why you get the drag larger than the laminar value. So we kind of analyzed that, why that is the case. And you can show actually, depending on what wave speed you use, this is the traveling wave the blowing and suction will put, and the induced b prime and u prime, the phase shift between u prime and b prime in relative to the blowing and suction you put is such that if you have a certain wave speed, you can actually have this is exactly the way you want. In this case, u prime, b prime will be a positive. And that is the case, then you can have the drag reduction. And if you examine that, this is a blowing and suction and u and v, so you can show that actually particular wave speed, in this case, the upstream traveling wave create the positive Reynolds stress, and that's what we've seen. Now, that led to us to examine the flow more carefully. What it does, the extra Reynolds stress that we're creating is actually additional pumping motion that created by the traveling wave. And I'm going to just show the, in this case, there is no mean pressure gradient. You got to just channel, and you start the pumping in the blowing and suction and traveling wave. This is a total mass is being created by this and reach this after steady state. If this blowing and suction was not traveling, we're just doing just up and down, because of the symmetry, there will be no net mass flux. But because of the asymmetry created by traveling wave, it produced, and plus the viscous effect, it produced a net mass flux. So this is additional pumping, so that the way we measure the drag for given mass flux to deliver, what kind of pressure gradient do we need? And because we've done some additional pumping through the blowing and suction, that we got the actually required power is less than what the normal laminar value. Well, later on, Lucchini look at this, I think it's a follow-up of work, and this is attributed to the steady streaming. This is in analogy to acoustic streaming that but this is actually the incompressible flow, but it's still the asymmetry created by the u prime, b prime actually is, but is that all? I mean, is that all the reduction is because we're pumping the extra due to this traveling wave? I don't think so. The turbulence case is actually a lot more than that. So we apply this is a turbulent flow, fully developed turbulent flow. Now, depending on the amplitude, of course, the amount of the pumping and the amount of reduction is depending on that. In this case, the small amplitude of blowing and suction, we get drag is reduced, but it's still larger than laminar. But one thing you notice that, look at this is a structure that disappeared. If you were just a pure pumping action, then we will see the similar structure, but you're just driving extra the mass flow in a downstream direction. But there's something more going on than this. If you do the higher amplitude, okay, in fact, even fully turbulent flow, also you can reduce the below that of laminar value. But you can see that the structure there's a totally disappeared in this case. So this traveling wave, yes, it does. It's actually extra pumping, but it's more than actual extra pumping. And if you look at the Reynolds shear stress you produce, remember that this is now ordinarily Reynolds shear stress in this case the upper wall is a positive, but because of the blowing and suction, you got a negative the Reynolds shear stress. That means less production. So less production means less fluctuation, and you actually reduce the whole structure. So in the case of the turbulent flow, there is both additional pumping due to the traveling wave, but also it does, because of the Reynolds stress it created, suppress the structure as well. So do we get really net reduction of these cases? The answer is a yes, but conditional yes, in the sense when we do the blowing and suction, it also requires an actual plumbing resistance and all that. But let's forget about that part for now. So just recall how much pumping power that we actually putting in. If you compute that, actually we get the net reduction. In other words, the way we define the efficiency, if eta is less than 1, that is actually get net reduction, and that is what is the number here. Just quickly, I want to conclude, and then I thought I was going to discuss a little bit more, but which was actually relevant to this question. But Hassan asked me to actually this evening that lead one of the group discussion topic of this about this self-sustaining process. Is this something that only exists in a low Reynolds number flows or not? I mean, that's still open question. I don't think so, but Julian Hunt strongly believe that is the case. So that's a very actually open question to about. And I'll just stop here.
We have 1, 2 quick questions. Yeah, short one.
Yeah. When you do the blowing and suction and the drag is below laminar drag, doesn't the velocity profile have an inflection point? So wouldn't that make it unstable? So prone to more separation and things like that?
You know, I haven't really had a chance to talk about this stability associated with that. We did some flow K analysis. Yes, it does induce instability. So that's why, in fact, we cannot keep in a two-dimensional flow. It becomes a turbulent flow. So actually, I mean, that's a very good point. And we are actually currently trying to design controller. Can we keep this instability from the controller, so keep it two-dimensional so they can have a laminar drag less than laminar with much less power that is